Now let's take a look at the EEPROM demo LabVIEW project. Here I have the microchip serial EEPROM connected up to MXP connector B. The VI is running right now. You have a number of actions that you can perform. You can read the entire array, write to the array, read the status register, or write to the status register. Use this button to control the write protect pin. Here you can read data from the array and display it in two different formats. Here you can specify values to write to the array and a starting address. Here you can specify a byte to write to the status register and then read it back. Let's begin by reading the entire array. Now as shipped, that is when you have a brand new device, all the values will read as 255 or hexadecimal FF. Use the index control to look at different values within that array indicator. 511 is the last address. Set this back to 0. Now at address 0, the value read back was 255. I'm going to attempt to write a 0 value to this location. So I want to write a 0 value at starting address 0. I'll select write array and then read back the entire array. Looks like no change here. Well, it would help to enable the device for writing, so I'll click that one again, try writing and then reading back. All right, here's the 0 that was successfully written and then read back, and that's again visible on the plot. Let's try a different starting address of 300, so that puts us in the mid section of the array. Try some different values here. I'm going to write 2 bytes this time of value 100 and 200, again starting at address 300. So I'll write those out, read back the entire array, and we see some activity right here. I'm going to go ahead and select address 300, and you see the value 100 and then 200 was written out to address 301. Let's try writing a few more bytes all at once. Give this a different value here. I'm going to go ahead and select 10 down there, and that automatically fills in all the in-between values with zeros. I'll just leave it that way for now. Now you can write up to 16 bytes, which is 1 page in a given write cycle. So I do a read back after the write operation. Again, the vicinity of starting address 400. Looks pretty good. Now at any time you can reinitialize the values to defaults, and that gets the front panel back to its original layout. Let's look at working with the status register. You can read back the status register after writing to it. So let me begin by reading the status register to see what's there. Looks like 00. Let me attempt to write a different value, and I will attempt to set the read-only write in progress flag. Read back, and that didn't work. Well, I guess I had the write protect turned on. Let's try again. So I'll write the status register, then read it back. But this is a read-only bit, so you can't set it. Well, let me try selecting BP0, which is block protect 0 flag, and this is a read-write bit. So I'll write it out, read it back, and sure enough, I was able to set that particular bit. Now I'm going to try writing to the very last address, address 511. The particular setting for the block protect bit means that the upper quarter of the array is presently write protected. Let me read back the entire array just to confirm what's already there, which is 255. Let me attempt to write a 0 value at this location. Read back, and no, that didn't work. So that's evidence that the write protection is working. Let me send the status register back to its original default value of 0. So write that and read it back. Let me try writing to the array and then reading back from the array. And here we have success. So at this point, I was able to write a 0 to that very last value. Well, now let's take a look at the details of the block diagram. I have three sections: the configuration section, the main loop section in which I control the write protect line as well as process changes on the action control. When a change is detected, you have a number of different options depending on the action that was selected. That's the case structure. Here you see the front panel indicators. And finally, when you break out of the main loop, you can do a MyRio reset. Now, along this track, these are the SPI related VIs. These are available under MyRio Advanced IO and then SPI. You begin by opening the appropriate channel either on MXP A or B, and then configuring the channel according to all of these values here in the cluster constant. I'm also using some low-level VIs to handle the digital outputs for both chip select and the write protect signal. These are also available under the MyRio Advanced IO subpalette under Digital IO. Now the chip select, I'm generating on DIO 0 on the B connector, and I'm using DIO 1 for the write protect signal. Now inside the main body of the loop, I'm looking for a change in the action control. To do this, I'm using the feedback node located under the programming palette. You can change the direction like this. The feedback node remembers the value of action on the previous loop pass, and when that's different, you generate a true value right here. So on the outer case structure, when that's true, you can perform an action. If it's false, simply pass the error cluster through with no activity. Now inside that outer case structure, I have the inner case structure, and this performs the desired sequence. All sequences begin by selecting the chip select of the double EEPROM, and all of them end by deselecting the double EEPROM. Again, that's manipulating the chip select. Now the action control value is fed to this inner case structure, and you have a case for each one of the actions, such as reading the array, writing to the array, and so on. Let's take a look at one of the more basic ones. Idle, of course, would be the simplest. It's just a straight pass-through. Reading the entire array works this way. You issue the read command for address 0. That looks like this pair of bytes that are written out to the SPI bus. You then request a read of 512 bytes. This is made available on these two indicators, one of which is the array indicator and the other is the graph. So let's look at this tunnel for a moment. Looking at another subdiagram such as write to array, I'm not feeding anything out, so therefore I used right click and use default if unwired. Now the first thing we need to do under writing to array is issue the write enable instruction and then toggle the chip select. The write instruction is formed this way. It's based on the starting address and the number of bytes to write. That is the actual byte values in that array. So I look at splitting the starting address into two pieces. Here, look under the data manipulation subpalette of the numeric subpalette. That's split number. That breaks up the 16-bit address into 2 bytes. Both high and low are available. Here I'm shifting that most significant address bit up several places, inserting the instruction for write operation, casting that into a 16-bit unsigned integer, and then using build array with the concatenate inputs option turned on to assemble the complete instruction. So we have 2 bytes worth of instruction followed by the number of data bytes to write. Disable the chip select to initiate the data writing process, and then wait for 5 milliseconds. So I have 5 millisecond wait encased inside a single panel of a flat sequence structure. That's available right here. And that allows me to get the error cluster to pass through that structure and ensure that the wait happens at the right time. Speaking of the error cluster, let's follow its propagation path through the entire block diagram. Again, the error cluster causes events to happen in a specific order. Eventually it emerges out the other side. We pass through this simple error handler and execute a myRio reset. Now I'm just noticing that my usual construct here is missing, so let me stick that in here. This way an error or pressing the stop button will break out of the loop. Also, I'm pacing the loop at 100 milliseconds. That means the front panel action control is being pulled at 10 Hertz. Now I'm going to finish up by showing you how you can add additional functionality to this case structure. Each of the subdiagrams is based on the values from this enumerated data type called action. I'll show you where you can find this type of a control. Right-click, I'm looking under Silver, Ring and Enumerated, and the enumerated control is located right here. I'm going to right-click on that and choose Edit Items. Here we see that each item has an associated integer value. Now you can insert or delete or move things around as needed. I'm going to insert a new item here called New Menu Item. Presently it's associated with value 0, but if I move it down to the bottom, now it's associated with value 5. Now I'd like to show you why it's advantageous to first begin by editing that enumerated control. Here we don't see any change, of course, in the case structure, but if I right-click and say Duplicate Case, especially if I find a case that's closest to what I would like to work on next, for example, supposing I wanted to use read array or read entire array as my basis for this. Now when I say Duplicate Case, you see that it's been duplicated and associated with that new menu item automatically. It's very convenient. I'm going to do a quick Control-Z to undo my previous step and show you another method. Here I'm selecting a sub-diagram. I'm going to say Add Case After. Now it's created an empty sub-diagram with that new menu item name.